All right, welcome to another deep dive.
Yeah.
This time we're looking at a really fundamental concept, I think, in the world of data,
Hmm.
and that is network throughput.
Yes.
It's the rate at which messages, move over a communication channel,
Yeah.
whether we're talking about, Ethernet or packet radio or whatever it is.
Yeah.
It's kind of the lifeblood of any connection, really.
It is.
And today we're going to try to really break it down and
Yeah.
understand what throughput really means,
Yeah.
what factors can affect it.
Yeah.
And so hopefully by the end of this session, you'll have
Yes.
a much clearer picture
Right.
of what exactly is going on when we're talking about throughput.
Yeah.
We've got a lot of different sources here today, so
Yeah, we do.
we're going to go pretty deep on this.
Great.
That's great. Love.
Okay.
So,
Yeah.
throughput is something that I
Wow.
think is really important for anyone who's using networks these days, which is basically everybody.
That's
Right?
true.
It determines how fast,
Yeah.
our online experiences are.
Right.
How smoothly they go.
Yep.
Whether you're trying to stream a movie
Uh-huh.
or transfer, important files.
Yeah.
It all comes down to throughput.
Absolutely.
And we measure this flow
Okay.
in a couple of different ways.
Yeah.
We'll be talking about bits per second,
Yep.
packets per second.
Mm-hmm.
But
Right.
it can get pretty complicated.
Sure can.
The world of network performance is pretty intricate.
It is.
So
Okay.
let's get started.
Yeah.
We're
Right.
we all want the fastest possible speed, right?
Of course, yeah.
When we're talking about networks.
Who doesn't?
So let's start
Mm-hmm.
talking about maximum throughput.
Okay.
But the thing is, when we say maximum, it turns out that isn't really just one number.
Right.
There's actually a few different ways to
Mhm.
think about maximum throughput.
Right.
We've got maximum theoretical throughput, asymptotic throughput,
Yep.
peak measured throughput,
Oh.
and maximum sustained throughput.
Mm-hmm.
And so
Okay.
I know it sounds like a lot of jargon,
Yeah, it does.
but these are really
Oh.
all different slices
Right.
of that same performance picture.
They are. Yeah.
So let's break them down
All right.
a little bit.
Yep.
So you were just talking about how the idea of maximum
Yeah.
depends a lot on
It does.
ideal versus reality
Exactly.
of the network conditions.
It does.
So
Yeah.
what's going on there
Well,
with
Yeah.
maximum theoretical throughput?
yeah, so maximum theoretical throughput is kind of like the
Right.
absolute speed limit, like on a highway.
Right.
It's the fastest that we could possibly transfer data,
Okay.
and that's
Yeah.
under ideal conditions,
Right.
like perfect laboratory conditions.
Yeah.
You
Okay.
know, this often gets tied to
Mm-hmm.
the raw capacity of the communication channel
Yeah.
itself.
Okay.
But there's a catch.
Okay.
Only systems that
Right.
don't break data into packets
Okay.
can really achieve this theoretical maximum.
Interesting.
And so,
So it's not really most systems.
right, so packet-based networks,
Yeah.
which are,
Right.
really the backbone of modern communication,
Yeah.
those inherently have overhead
Okay.
that make this ideal
Right.
virtually impossible.
Right. To reach.
Exactly.
So it's
Yeah.
almost like a dream.
Yeah, so we see these advertised speeds,
Yeah.
right? Like, oh, you can get, a gigabit per second or whatever.
Yeah.
But it's important to remember that
Yeah.
that's not
Right.
really attainable
Right.
in the real world.
Yeah. Because of that packet overhead.
Right. We're already starting out
Yeah.
at a disadvantage. You know what I mean?
Yeah, it's kind of a ceiling
Right.
that you can't really ever touch.
It's a ceiling you're unlikely to ever truly touch.
Yeah. Yeah. Yeah.
Okay, so
Yeah.
theoretical limit
Mm-hmm.
is really more of just a benchmark
Yeah.
than,
Right.
a
More or less.
real expectation.
Yeah.
For most
Yeah.
people.
Yeah.
Okay, so then let's talk about asymptotic throughput
Okay.
or asymptotic bandwidth.
Yeah.
This one sounds
Mhm.
a little bit more grounded in reality,
It does. Yeah.
especially for those packet-based networks.
Mm-hmm. So how should we think about this one?
So think of asymptotic throughput
Okay.
as the maximum speed that you would observe
Right.
when a network is under a lot of stress,
Okay.
either from like transferring a massive amount of data
Yeah.
or from having a ton of active users.
Okay.
It's the point where adding more load to the network doesn't really increase the throughput anymore.
So it kind of plateaus?
It sort of plateaus, yeah.
Sure.
And typically how we measure this is by either, flooding the network with large data streams, or we do it through simulations.
Okay.
And it's important to note that any other traffic that's present on the network during these tests can influence the results.
Interesting.
So there's sophisticated tools out there that are used to, predict and optimize the performance of these complex systems under a lot of load.
Right.
They want to make sure that even when things get really busy, the data is still flowing efficiently.
Right.
This is critical.
Yeah.
When you're designing, robust and scalable network solutions.
Absolutely. So it's really about seeing what the system can handle when it's pushed to the limit.
To its limits,
Okay. All right. So then we've got peak measured throughput.
Okay.
Which sounds a lot like what you might see in like a speed test.
It does, yeah. So peak measured throughput is the highest data transfer rate you might see in a very short burst of activity. In a real or simulated environment.
Okay.
It's like capturing that fleeting moment of top speed.
Right.
And so this is useful for understanding how things perform when you're using applications that involve like short, intense bursts of data.
Yeah.
But it's not necessarily reflective of the consistent performance you'd see over time.
Right. So it's not the whole picture.
It's not the whole picture.
Okay.
Yeah.
And then finally, we have maximum sustained throughput. And this one seems like it might be the most relevant for everyday use.
It is. Yeah. Maximum sustained throughput is the average data transfer rate that you can maintain over a long period of time.
Right.
So for networks that are constantly handling traffic, this is the most accurate indicator of how they're actually going to perform under really heavy continuous load. Maximum sustained throughput often converges with asymptotic throughput. But it's also worth noting that sometimes this metric can be used to sort of mask techniques like packet shaping, where the traffic is intentionally slowed down at certain times.
So looking at sustained performance is often more telling than just a peak number.
It is.
Okay.
Yeah.
All right. So we've got all these different ways of thinking about maximum performance. But throughput is also really about how effectively we're using the communication channel, right?
Exactly, yeah.
And so that's
where channel utilization and efficiency come into play.
You do.
And so while throughput itself might sometimes be expressed as a percentage of the total capacity, channel utilization and efficiency are more precise ways of describing how well we're using that available bandwidth.
Yeah.
So what is channel efficiency?
Okay, so channel efficiency.
Or bandwidth utilization efficiency.
Or bandwidth utilization efficiency, right?
Yeah.
That's basically the percentage of the net bit rate that's actually being used to deliver the useful data that you care about.
Right.
So for example, if you have a 100 megabit per second Ethernet connection, and you're getting 70 megabits per second throughput for your data,
then your channel efficiency is 70%.
Okay, that makes sense.
Yeah.
And so channel utilization then is just kind of a slightly broader measure.
Yeah, so channel utilization is looking at the total use of the communication channel.
Okay.
And this includes not just the data bits themselves, but also the overhead.
Okay.
And that overhead includes things like the preambles, the headers, the acknowledgments that need to be there for the protocol to function. So in a point-to-point link where only one device is actively transmitting data.
Okay.
The maximum throughput can get very close to the physical data rate.
Yeah.
Because the channel utilization can approach almost 100% with only small gaps between the data frames.
Right. Right. So can you give us like a tangible example of how that overhead impacts the achievable throughput?
Okay, yeah. Let's go back to that 100 megabit per second Ethernet connection.
Okay.
The maximum size of an Ethernet frame is 1526 bytes.
Okay.
But within that frame, only 1,500 of those bytes are typically the actual data payload.
Okay.
The other bytes are overhead.
Okay.
So that includes 8 bytes for the preamble, 14 for the Ethernet header, and 4 for the frame check sequence.
Okay.
Which is also called the trailer.
Right.
Additionally, there's a mandatory interframe gap of 12 bytes between each frame.
Okay.
So if you calculate this out, the maximum channel utilization, considering all of this necessary overhead, is around 99.22%.
Wow.
However, the maximum throughput or the channel efficiency, which is, the percentage dedicated to the actual data, works out to be about 97.5%.
Okay.
So even though the protocol needs this overhead to function reliably, it does reduce the amount of pure data that we can transmit in a given time frame.
Yeah, that's interesting how those seemingly small bits of overhead really add up.
They do.
To something noticeable.
Yeah, they do.
Okay, so let's shift gears a little bit and talk about some of the real world factors that can limit the throughput of our communication systems. Because it's not just about these theoretical limits.
It's not.
And the protocol efficiencies, right?
Not at all.
Yeah. So there are a lot of things.
Numerous factors.
That can create bottlenecks and reduce our achievable throughput.
Yeah.
And we can kind of broadly categorize these limitations as analog limitations. Considerations related to integrated circuit hardware.
Right.
And then, the complexities that arise in multi-user environments.
They do.
So let's dive into the analog limitations first. It might seem counterintuitive that, analog properties would affect digital data transfer.
Okay.
Over wires.
Yeah. So even though we're dealing with digital information, the signals that travel over the physical media, like the wires, are fundamentally analog electrical signals.
Right.
So these analog characteristics, they impose limits on how much information we can transmit reliably.
Interesting.
The Shannon-Hartley theorem actually describes this mathematically.
Yeah.
And it shows that the theoretical capacity of a channel depends on the bandwidth, which is the range of frequencies that it can carry, and the signal-to-noise ratio.
Right.
What many people find surprising is that the usable bandwidth of even common wired systems like Ethernet cables is actually relatively limited, often around 1 gigahertz.
Right.
Even the traces on printed circuit boards. They have similar bandwidth constraints.
Okay. So even though we're talking about the digital world.
Right. Even in the digital world.
These analog properties play a big role.
They do.
So what are some of those key analog limitations?
Okay. Yeah. So there are several factors that come into play here.
Yeah.
We have something called RC losses. Which are caused by the resistance and the capacitance of the wires. They act like filters that attenuate high frequency components of the signal.
Right.
And so they effectively limit the data rate. Then there's the skin effect. Which is a phenomenon where at higher frequencies, the electrical current tends to flow primarily along the surface of the wire.
Right.
And that reduces the effective cross-sectional area.
Right.
And thus increases resistance. And that becomes dominant in a Cat5e cable. at around 100 kilohertz.
Okay.
Then you've got termination and ringing.
Okay.
Which is super critical.
Okay.
Especially for long cable runs where you can have signal reflections that interfere with the signal and corrupt the data.
Okay.
And of course, in wireless communication, you have a whole host of additional analog channel effects like path loss, feeding interference that all impact the signal-to-noise ratio.
And the available bandwidth.
So that's a lot to consider.
It is.
It's just at that physical signaling level.
It is.
So then let's move up a layer and think about the integrated circuit hardware that powers our networking equipment.
Right.
How do the chips themselves become limitations?
Okay, so the integrated circuits within our routers, switches, and network interface cards, they have their own performance limits.
Right.
They have, finite processing power.
Yeah.
And they can only drive a certain amount of current.
Okay.
And so when they don't drive enough current, that can lead to a reduced signal-to-noise ratio.
Okay.
Especially on links with significant
capacitance.
Okay.
Think about a high-performance router handling traffic for a large network. It needs to perform billions of lookup operations every second to determine the correct path for each incoming packet.
Wow.
And so if the processing capabilities of the router's hardware aren't sufficient to keep pace, it's inevitably going to become a bottleneck.
Okay.
Which will limit the overall throughput.
Right. So the brains of the network.
Right. Exactly.
Have to be strong enough.
To handle it all.
To handle the flow.
Exactly.
Okay. So what other IC hardware considerations? Expert speaker.